Today we're going to be talking about finding the inverse of a matrix. Now, matrices don't naturally commute, meaning A times B does not necessarily equal B times A. So matrices help with operations like that. Also, the inverse of a matrix is what gives us matrix division. Not every matrix is invertible, which is the verb version of inverse. You have to meet very specific criteria. Two things. First, it must be square. The second thing, the determinant must not be 0. If the determinant is 0, you have a non-invertible square matrix. They do exist. I'll show you why that wouldn't make sense here in a second. Let's go through the steps of how to figure this out. Now, mathematically, it sounds very complicated, but the rules themselves are fairly simple. The first thing we've got to do is find the determinant. So remember, the determinant is found by going A times D minus BC. Remember, that's the main diagonal, subtracting out the other diagonal. That's the first step. If that is 0, you can stop and say it's not an invertible matrix. The next thing you've got to do is switch A and D. So in our new matrix, B and C stay the same for now, but we switch the positions of D and A. That's all you have to do with them. You don't have to switch the signs or anything. Just physically write them in the other spot. The next thing you've got to do is switch the sign of B and C. So make them negative. If they were negative already, you would make them positive. The last thing you've got to do is go ahead and multiply the matrix by 1 over determinant. So your final answer will be 1 over the determinant multiplied by that matrix. So for example, you could have the matrix 2, 5, 0, 1. If we were to find the inverse of that, we'd first have to take the determinant. So that would be 2 times 1 minus 5 times 0. So that'll be 2. So this is an invertible matrix. We then go ahead and flip our 1 and 2, switch their places, and we make the other two things negative. Negative 0 is just 0, so we can go ahead and get rid of that part. We then multiply the entire matrix by 1 over 2. Now, I'm okay if you stop here, but make sure that you realize that if you need to use this matrix at all, you have to multiply the 2 into it. So for all intents and purposes, this matrix is 1/2, negative 5 over 2, 0, and 1. I'm going to do something you don't necessarily have to do in your homework, but I want to prove a point. We're going to take our original matrix and multiply it by our new matrix. All right. Let's go ahead and just multiply them together and see what happens. So remember matrix multiplication. We multiply the first row by the first column and add them together. So we get 2 times 1/2 plus 5 times 0. We do the same thing for the next row and the next column to find the next point. So that'll be 2 times negative 5 over 2 plus 5 times 1. Our next point, next row, next column. So we have 0 times 1/2 plus 0 times 1. And our last one, this row, this column. So that'll be 0 times negative 5/2 plus 1 times 1. We go ahead, do some math. We end up with 1, 0, 0, 1. This is the identity matrix. So note that when you have a matrix, you multiply by its inverse, you get the identity matrix. This is also true if you multiply it the other way, because remember, matrices don't commute. So the inverse first times the original matrix will also give you the same result. That's just an important thing to keep in mind, a very important property of inverses of matrices. Now, these rules work for 2 by 2 matrices, but they don't necessarily work for things of higher order. I'm not ever going to expect you to do finding the inverse of a matrix of higher order without a calculator, but I'm going to explain just a little bit of the theory here first. So here's what's happening when you do that. We're going to just use a 3 by 3 matrix because it's the next smallest, GHI. So the first thing you have to do is find the determinant of it, of this matrix. We're going to call that number K. We're going to claim that the determinant of this is equal to K. I just picked that number out of a hat. I didn't take the time to, write out the formula for it. If you're wondering how to do that, check out yesterday's video. From there, we go ahead and switch the rows and make them the columns. This is called the transpose of a matrix. You'll notice that we switched the other elements in the 2 by 2 as well. This is similar. From there, we do what's called the cofactors, meaning you find the A, you cross out the other columns. You would then find the determinant of this matrix. Oops, there goes my chair. Once you do that one, you'd have to do the next one, cross out the rows and columns that it's in, figure out the determinant of this matrix, and so on and so forth. You'd have to do that 9 times. I think that's too much work for students for very little payoff. And that's not even the end, because after you figure out all of those determinants and put them in for these elements, you then have to make some of them positive and some of them negative in a grid pattern like we do with our 2 by 2. And then you have to multiply everything by 1 over the determinant. That's too much, way too much, too prone to error. So go ahead and go to desmos.com/matrix. That will pull up the matrix calculator. You could go ahead and build yourself a matrix of any size and put in numbers. The numbers themselves don't really matter. 4. Okay. Hit enter. Then from here, you could figure out the inverse of it by going A inverse. Hit enter. And it's giving me an error. I wonder why. Anyway, that's how you do it. You could probably figure out the determinant of the same thing. Ah, that's why. It's bringing back a determinant of 0. Therefore, it's not invertible. All right, let's just try another matrix just for funsies. We'll keep it smaller this time. Let's figure out the determinant of b, just to see if it's invertible. Oh, it's another one saying 0. Let's just change one element and see if that makes a difference. Oh, there we go. That one's invertible. So then we can go ahead and figure out clear to the -1. Oh, and there we go. It gives us our determinant back. As always, let me know if you've got